Mathematics. Why was it invented? Well, to describe things around us numerically. We have two number systems. One is the real number system and the other is the imaginary number system, which both form the complex plane. Today, we will be talking about the imaginary number systems, its history and how it has dazzled great minds for thousands of years, and how it started the greatest debate among mathematicians. In olden times, mathematicians used to use algebra with geometric visualizations, which worked to some extent. Then came a problem so hard that it was deemed impossible to solve. Cubics confused the mathematicians for so many years that the civilizations who encountered these cases all came back empty handed. Among the olden mathematicians was a named Luca Pacioli. He was the teacher of the famous Leonardo da Vinci. He wrote a book named Summa de Arithmetica, which was the synthesis of the mathematical knowledge known in his era. In this book is a section of cubics. Luca Pacioli concluded these problems as impossible to solve. This comes as a surprise because if we remove the cubic term, it becomes a quadratic equation, which had already been solved for thousands of years.
Take, for example, the equation x squared plus 26x equals 27. Ancient mathematicians would think of the x squared term like a literal square with sides of length x. And then 26x, well, that would be a rectangle with one side of length 26 and the other side of length x. And these two areas together add to 27. We can take this 26x rectangle and cut it in half. So now I have two 13x rectangles, and I can position them so the new shape I create is almost a square. But I know the dimensions of this section, it's just 13 by 13. So I can complete the square by adding in a 13 by 13 square. Now, since I've added 13 squared or 169 to the left-hand side of the equation, I also have to add 169 to the right-hand side of the equation to maintain the equality. And it is equal to 196. Now, the square root of 196 is 14. So I know that the sides of this square have length 14, which means x is equal to 1. X equals 1 is a solution, but so is negative 27.
For thousands of years, mathematicians were oblivious to possible negative solutions because they were using a geometrical description for these algebraic problems. In geometry, having a negative unit is a bit confusing because what would it mean to have a negative length or a negative area perhaps? Mathematicians were so unwilling to the idea of negative quantities that to avoid any negative coefficient in these problems, the mathematicians will derive 6 different formulas of quadratic to get a positive number. The same was done for the cubic. In the 11th century, a Persian polymath, Omar Khayyam, derived 19 different cubic equations to keep the coefficient positives. He even found some solutions by considering intersections of shapes like hyperbolas or circles, but couldn't generalize a solution for the cubic. 400 years later, a mathematician starts to formulate the solution to the cubics, Scipione del Ferro. He was appointed in 1496 at the University of Bologna. In Del Ferro's time, mathematicians knew that the general cubic equation can be simplified in one of two cases, called the depressed cubic. It is basically the cubic equation without the x squared term. Somewhere around 1510, he found a way to solve the depressed cubics. And what actions does he take? He locks it away. Because in 1500, a mathematician's job was always in a competition, because other mathematicians at any time could challenge you for your position, basically like a world heavyweight champion. Sports like WWE or UFC, the one who solves most questions correctly wins the position and the loser mostly publicly humiliated. As Del Ferro assumed, no one else in the world has ever solved the depressed cubics, hence securing his own position. He kept it a secret until his end times. Only on his deathbed in 1526, he discloses his secrets to his pupil, Antonio Maria del Fiore. Now, Fiore wasn't as bright as his own teacher, but he was ambitious. After the death of Del Ferro, Fiore goes out to the public and boasts about his mastery in mathematics. He went as far as to challenge even a mathematician who recently moved into his hometown. Who was the mathematician that Fiore challenged? He was Niccolo Fontana Tartaglia. Fontana wasn't a stranger to affliction. In the War of Cambrai, King Louis XII's troop invaded his hometown, where a French soldier sliced his jaw, leaving him with a stutter, hence the name Tartaglia, which means stutter in Italian. He, through self-teaching, became a respected mathematician in his society, and after Fior challenged him, all which he had worked on was at stake. Both gave each other 30 sets of questions to solve in 40 days. Fior, having Scipioni's solution to the depressed cubics, gave Fontana questions of only depressed cubics. Fior wasn't able to solve any questions, while Fontana solved all 30 questions in just 2 hours. Before the challenge, Fontana learns about Fior having the solutions to depressed cubics. But he had skeptical views about Fior. He said, "I did not deem him capable enough to find such a rule on his own." But word was that another mathematician had given him the solutions, which was more plausible or believable. So knowing that a solution to the cubic exists, Fontana went on to solve the equations, which he did. Mathematicians were eager to know the solutions of the depressed cubics, but Tartaglia disclosed nothing, not even a single question of the competition, to anyone. But one mathematician was persistent enough to get the solutions out of Fontana. Girolamo Cardano was able to receive the solutions to depressed cubics, but he had to swear an oath to Tartaglia that he will never publish this or tell anyone about the solution, and to only convey it in codes so that after Tartaglia's death, there will be no one that will understand it. Cardano was thrilled and started using Tartaglia's algorithm. He wanted to not only attain the solution of the depressed cubics, but the whole cubic equation with the x squared term. And surprisingly, he discovers it. Cardano was amazed by his solutions to a problem that had many mathematicians perplexed for so many years, so much so that he wanted to publish this. Because Cardano wasn't just a mathematician, he was also a physicist, astronomer, chemist, biologist, and more. For him, the credit was more important than the position. But only one obstacle stood in his way, which was the oath that he took from Fontana. So he didn't publish it. This act of not publishing the solutions would have sealed the deal. But in 1542, Cardano travels to Bologna and meets another mathematician who was the son-in-law of another great mathematician named Scipione del Ferro, the first man to ever solve the depressed cubics and pass it on to Antonio del Fiore. On his deathbed, Cardano views Del Ferro's notebook, which was shared with him on his tour. Now Cardano can publish the solutions without breaking the oath. Some years later, he publishes the book named Ars Magna, an updated compendium of mathematics. Written in 5 years, may it last 500. Following the publishing of this book is the greatest feud in mathematical history, involving Cardano and Fontana exchanging insulting letters and statements and having a debate publicly. But as we see it, Ars Magna was a phenomenal achievement. In the Ars Magna, Cardano faces some problems which cannot be solved in the normal way. For example,
x cubed equals 15x plus 4. Plugging this into the algorithm yields a solution that contains the square roots of negative numbers.
He asks Fontana about this case, but Fontana implies that Cardano didn't use the formula correctly. But in reality, Fontana himself didn't know why this happened. Cardano finds that there must be a square with sides 5 units, but having an area of 30 units squared, which is geometrically impossible, because he now had to add -5 area into that square. But it could be proven through further simplification that there is a real answer, which is 4. So why couldn't the general cubic formula work on this cubic equation as well as it has for others? Cardano avoids these cases and states that the idea of roots of negatives is as subtle as it is useless. Another mathematician named Raffaele Bombelli picks up where Cardano left off, the roots of negatives, observing in his book L'Algebra that the square roots of negatives cannot be called either negative or positive. He considers that the roots of negatives can be identified by a new type of number, one ordinary number that is either added or subtracted to a product of ordinary number with the root of -1. If Cardano equation is further solved, it could be seen that the two roots simplify to 2 plus minus root of -1. By adding these two, we get the real answer of the equation, which is 4. Cardano's method does work, but only by abandoning the geometric ways of explanation can we solve these kind of equations. René Descartes makes use of these numbers and calls them imaginary, a name that will be used in the future to denote these kind of numbers. That's why Leonhard Euler introduces the letter I for the root of -1. This is not the only place where the complex numbers show. In 1925, Erwin Schrödinger, in search for his phenomenal wave equation, which could explain the behavior of quantum particles, called the Schrödinger equation, features within it a symbol I. Schrödinger wasn't happy with the symbol I showing up in his formula. He states, "What is unpleasant here, and indeed to be directly objected to, is the use of complex numbers. The wave function psi is surely and fundamentally a real function." Freeman Dyson said Schrödinger puts the square root of -1 and it suddenly made sense. Suddenly it became a wave equation instead of a heat conduction equation. He further states, and that root of -1 means that nature works with complex numbers and not real numbers. Who would have thought that a complex solution of the cubics that took thousands of years to solve would be so important and fundamental to our description of reality?